Okay.
Welcome back, everyone. So today it's my pleasure to welcome Linfeng Wang, who will be talking about measure transport with the Kalman-mean embeddings. Yeah, thank you, Linfeng.
Okay, thanks for your introduction. And so, hello everyone. My name is Linfeng, and I'm from King's College London. So first, I have to thanks the Turing Institute for organizing such nice seminars, and it's my pleasure to give our talk about the measure transport with kernel mean embeddings here. So this is project collaboration between me and my PhD supervisor, Nicholas Newskin. So now let's start. So in this talk, I will first introduce our the problem we are working on and the motivation of it. And secondly, we will talk about the construction of our algorithm. And finally, I will show some numerical experiments to check the performance of this algorithm. So the main problem we are working on is called the score-free sampling problem. So specifically, we are just given some samples from the prior and the formulas for log likelihood function. And then our objective is to generate samples for the probability distribution of posterior, where the relationship between the prior and the posterior is given by this Bayesian formula here. And we use the notation pi0 to be prior and the pi1 to be the posterior. And you will see why we use the notation like this later. So why this problem is called score-free? Because the score function is actually defined by the gradient of log of the probability distribution. Here, we don't have the formula for any distribution for prior, both prior and posterior. So that's why we call this problem the score-free, and we are doing sampling. So here is a sketching to illustrate this problem, that we're just moving samples with law of the prior to the samples that follows the law of the posterior. And then, so why we would like to study this problem? Because this score-free sampling problem is a fundamental problem for particle filtering. So maybe let me introduce about the particle filtering here a bit. And so the particle filtering is based on a hidden Markov model, which is a time series described by these two stochastic equations, where the hidden states is transformed by the model, by the forecast model perturbed with some model noise, and the observation is calculated by apply the observation model perturbed with some observation noise. And the objective of particle filtering is that so given the samples, we call this the posterior at the time step k. And first, we move these samples according to the forecast model, and of course, produced with some noises. And then we treat this, move the samples as a prior in our context we introduced before. And we would like to generate samples for the posterior at the next step, and the likelihood function is exactly given by the observation noise here. And you can see immediately that this is exactly the problem we defined at the beginning of this talk. And that's why we need to study this score-free sampling problem. And for a simple, the easiest example of particle filtering is called the Kalman filter, which the hidden Markov model is just defined by whose forecast model is just linear, and the observation model is also linear, like here. And all of the noise, both of the model noise and the observation noise, are just Gaussian. And of course, we have to also initiate our prior also to be Gaussian. And in this simplest case, we can actually write down the analytical solution for this filtering problem, which means we can actually write down the probability distribution formulas for each time steps, for the posterior at each time steps. And so this Kalman filter is used quite common in the time series simulation direction. And the most advantage of it is that it is very robust and computational with very small computational cost, and even in high dimensions. But the disadvantage would be just, of course, not all of the filtering problem is common. Like, so the forecast model and the observation model could be nonlinear. And of course, the noise could also be non-Gaussian, and also the prior could be non-Gaussian. So when it's not linear and Gaussian, the Kalman filters lose the tractability somehow. So now we move on to the second part of this talk. So how do we solve this score-free sampling problem then? So, so in our work, we focus on solving this problem in continuous setting, which means we are finding a velocity field Vt here, so that we can move the samples by this ODE here. And the samples should follow the path of this path of distribution we choose here. So in this path of distributions, as you can see, when t is 0, it recovers the prior pi0. And when t is equal to 1, it recovers the posterior by Bayesian formula. So, and our idea is to matching the transported measure with this path of distributions. Here, we have plots. We have sketching something to illustrate this main idea here. But unfortunately, we cannot put it on the PDF by LaTeX. So maybe I just quickly show it here. So it's like, so as you can see in this, sorry, can you see my screen now here?
Yeah, we see it. Yeah.
So it's like, so the idea is like we move the samples by the velocity field, and it should follow the path of distribution at each time here. And when t is equal to 1, we reach our posterior. So, okay, let's get back to our main talk here. Yeah.
Sorry, I think the demonstration wasn't seen, right? Only the slides.
Oh, okay. So maybe show it again.
I only see the slides. Yeah.
Oh, sorry. Where is it? So, yeah, can you see it now?
Yes, yeah, so yeah.
So it's like, so this histogram is samples we are moving, and we move it by the velocity field. And practically we can just choose a time discretization, time schedule for like we using a Euler scheme. And move the samples according to the velocity field and follow the path of distributions. And when time is equal to 1, we get our posterior and the corresponding samples. So, okay, maybe now let's get back to our main talk. Yeah. Yeah. Okay, so how can we solve this score-free sampling problem in continuous setting? So in this idea, an immediate solution for this would be we can use the continuity equation. So the continuity equation connects the path of the distributions and the velocity fields like this. So the time derivative with respect to the path of distribution is equal to the minus of the divergence of the distribution multiplied with the velocity field. And here, if we calculate the time derivative in our setting, the time derivative for the path of distribution in our setting, we can get this continuity equation in our setting. And that means if we can find a solution of velocity field V to solve this continuity equation, then it could solve our sampling problem before by transporting the measures by the ODE. However, the challenge can be easily seen here is that after some derivation, we can see this continuity equation actually involve the score functions here. So this means we actually cannot write down the continuity equation explicitly. So that's what our work will do then. I mean, how to solve this challenge here. So maybe before we go to the solution, let me show a quick example of application of this continuity equation. So recall that we are talking about the Kalman filter. Actually, the Kalman filter can also be converted into the continuous settings, which means we have the prior as Gaussian and the likelihood as quadratic form. And then actually we can also write down the solution for this Kalman filtering problem analytically, also in continuous setting. So we can so one of the solution for the continuity equation in this case is called the Kalman-Bucy filter equation here. It is linear in X, and so the Kalman-Bucy filter equation also plays an important role in our discussion later. So yeah. Now let's move on to answer the question about how can we solve the challenge about the score-free setting. So the main idea of our work is that actually the continuity equation is somehow like we are matching every information from the probability distribution at each time step. But now, because we don't have the formula for the probability distribution, so can we somehow lose some information from the probability distribution? So the idea would be we just find some statistically computable information and compare this information of probability distributions so that it can also it can still somehow conclude that the transporting measure can follow the path of the distributions. So for examples, like the moments information, so we can just compute the empirical moments from the samples only, right? So in our work, the statistically computable information we will use is called the kernel mean embeddings. And this kernel mean embeddings is defined by a feature map that maps the probability distribution to a function. So by this formula here, as you can see, we have a probability density distribution rho, and we maps it to the integration of the kernel function against the measure rho here. It is still a function. And so it is very clear that numerically we can estimate the kernel mean embeddings by Monte Carlo idea. And so now the problem is, how much information did we preserve from the probability distribution so that we can make sure we can conclude the transport measure should follow the flow of the path of the distribution. And specifically, the question would be like, so if the kernel mean embedding of two probability distribution are the same, can we say, can we conclude that the probability distribution itself are the same? Generally, the answer would be no, and it is significantly depend on the choice of the kernel function. So for example, if we just take the quadratic kernel function like this, and the only thing that kernel mean embedding can learn from the probability distribution is their first moment and the second moment. And actually, this proposition also applies to higher order polynomial kernel functions, which means we can take nth order polynomial kernel functions, and the corresponding kernel mean embeddings only learns the moments up to nth order. So yeah, but that's not the end. Actually, we expected the kernel mean embeddings can further capture all of the information from the probability distribution. Unfortunately, we have learned that there is a class of a positive definite kernel function called the characteristic kernel that is defined just to be injective, which means this feature map is injective. That so if the kernel mean the equivalence between the kernel mean embedding of two probability distributions can straightforwardly implies the equivalence between the probability distribution. For example, the Gaussian kernel, which is quite common kernel used in kernel theory, is a characteristic kernel, and we will use it a lot in our numerical experiments. So now we get back to our main problem. So if we have such statistically computable information, can we further derive something similar to the continuity equation? The answer would be yes. And here, in our work, we call this kernelised continuity equation. And the derivation will be very simple here. So we can so here is the continuity equation I copied from before. And actually we can just do the kernel mean embedding for the both sides of this continuity equation, which means we multiply the kernel function on the both sides and do the integration. And for the left side of the equation, we can do the integral by part. And this gradient term goes to the kernel functions. And as you can see here in the kernelised continuity equation, everything here can be estimated by Monte Carlo idea then. So remember that in the continuity equation, there was score function. It was very hard to calculate a velocity field solution from the continuity equation. But here we can at least estimate each term numerically, and we could try to find a solution with respect to V in the kernelized continuity equation here. It is clear that the kernelized continuity equation is much weaker than the continuity equation, because in the derivation here, you can see that the kernel function is just a test function. To make the opposite derivation to be satisfied, we have to take all of the possible test function, but here we just take the kernel function. However, actually we can actually the opposite direction can also to be satisfied if we choose the kernel function to be characteristic, because actually the kernel continuity equation somehow means we are matching the kernel main embeddings at each time step. And if we choose the kernel functions to be characteristic, this will be immediately implies that the equivalence of the probability distributions. So yeah. And so now the problem is, how can we find a solution for velocity field for the kernelized continuity equation? And here we just choose a very good representation for velocity field V here, and where this CT here is can be choose to be any positive definite matrix. But in our work, practically we just use this CT to be the covariance matrix from samples, and then we plug this representation of velocity field in the kernelized continuity equation, and then this leads to an inverse problem with respect to alpha here, where this operator generated by capital G is a new positive definite kernel function. Now you can see if we take a finite, if we look at this this new inverse problem in finite sample case, which means we just take Monte Carlo estimation for pi t here. It's actually just a linear system, so it would be very easy to solve this with respect to alpha then. And however, before I goes to the algorithm, I need to mention that there is a practical problem for this formulation yet, because this operator generated by capital G is actually compact in L2 space. So from functional analysis, we know the eigenvalue of this operator would accumulate at 0. So that means the eigenvalue of its inverse will be accumulate at the infinity. This will make the algorithm very unstable. And so practically, we have to plus a very small regularization term to the left-hand side of this inverse problem. Now, our inverse problem here is well posed, and we can solve it with respect to alpha and find exactly a unique solution. So to summarize, to solve the score-free sampling problem, we are doing in the continuous setting, and we are exactly solving this mean field dynamics here. And so here, we first solve the inverse problem here with respect to alpha. And after we have alpha, we'll plug it back into the representation of the velocity field. And then we can move the samples with this velocity field here. So as you can see here, everything here we can estimate by Monte Carlo. It would be very nice now. And sorry, here is our algorithm. And so we take the Monte Carlo estimation for the measure, and they take it, and we take the Euler scheme. So we just subdivide the time interval from 0 to 1 uniformly. And for each time step, we first compute the covariance matrix. And then we compute the gram matrix for the new positive definite kernel capital G. And then we compute the vector representation for the right-hand side of the kernelized continuity equation, and put them into the inverse problem we would like to solve. And then we solve this linear system. We have alpha, vector alpha, and we take this alpha back into the representation of the velocity field, and then we move the samples by the multiplication between the velocity field and the time step. So yeah, that's our algorithm. We call it the KME-dynamics. And so finally, I will show some numerical experiments for this algorithm. So first, here are some toy examples where we have Gaussian prior and the Gaussian posterior in the first plot. And in the second plot, we move the Gaussian mixture prior to the Gaussian mixture posterior. And in the last plot here, we move the Gaussian prior to a Gaussian mixture posterior. So we can see from the plot here that the KME-dynamics can work very well in the modes translation and splitting case. And so in this next toy example, we have the Gaussian prior and the school normal posterior. So here I want to recall our discussion about the choice of kernel we talked before, that if we choose the kernel function to be quadratic, then the the kernel mean embeddings can only learn the first moments and the second moments from the probability distribution. So this inspires us that actually for Kalman filtering is actually also only about the first moments and the second moments. So can we somehow show the KME-dynamics with the quadratic kernel is the same as the Kalman filtering somehow? Yeah, the answer would be is yes. In our paper, we provide a proof for this. So if we choose a kernel function to be quadratic in the KME-dynamics, and the prior is Gaussian, and the likelihood is quadratic, then actually we can just compute the velocity field out, and it's exactly the same with Kalman-Bucy filter equation. And here in this toy example, it provides a numerical evidence for this. So if we use a characteristic kernel, the KME-dynamics can learn the screwness very well. But if we use a quadratic kernel only, it seems the KME-dynamics can still be trapped in the Kalman filtering case. And so before I go to the next toy example, I want to give some introduction on it. So in the next toy examples, we focus on the case that moving the Gaussian prior to the Gaussian posterior. And we would like to somehow qualify the performance of the KME-dynamics by checking the estimated normalizing constant for the posterior and comparing it with the true value of it. And so, so before I show the results, there are two extension tools for the KME-dynamics. The first one will be, actually we can plus an extra term we call the baseline vector field in the representation of VT and make some corrections in the right-hand side of the kernelized continuity equation, and everything else in the derivation of KME-dynamics will be the same. So this means that so if we have some pre-knowledge about the particle filtering, for example, if we have already known that the likelihood function is somehow quadratic, we can just plus a known part in the representation of velocity field. So this method can help to improve the KME dynamics a lot. And another extension to KME dynamics is called the importance sampling KME dynamics, where we just replace the perfect Monte Carlo estimation for the measures by assigning some weights to the samples and make some corrections for the measures. And for this, and for sequential importance resampling, is just we didn't do any transporting in this method, but just do the reweighting for the samples. We calculate the weight for the next step and do the resampling. So let's now look at the numerical results here. So in the first plot, we show the true normalizing constant in the black solid line here. And so we check the performance of KME dynamics with respect to the dimension. And as we can see here, the KME dynamics is much stable than the sequential importance resampling. And when the number of particles is not so much, the KME dynamics can outperform the sequential importance resampling, even in high dimension. And in the second plot here, against the normalizing constant estimation with respect to the sample size, as we expected, when there are more sample sets used, all of the method performs better. And as expected, the sequential importance resampling get almost perfect when the number of particles is very large. However, there is a high variance for the sequential importance resampling. Here, the blue variation here is the error bar for the sequential importance resampling. However, for KME dynamics, it is very stable. And we can see that the importance sampling scheme can also improve the KME dynamics a lot, and even make the KME dynamics goes to perfect. And in the last plot here, we plot the normalizing constant against the time schedule, against the number of time steps we choose. So as we expected, with more number of steps we used, the performance gets better, and especially the importance sampling scheme can reduce the number of steps we need to use a lot, and both the extension for KME dynamics can improve the KME dynamic, the performance for KME dynamics a lot. So in the last experiment, I will get back to our motivation about the particle filtering. So specifically here, we use the hidden Markov model defined by this. So the forecast model is given by the Lorentz systems. So we implement this dynamics by the fourth order Range-Coulter method. And so for observation model, we just use it to be linear. And for the model noise and the observation noise, they are both Gaussian. And as we can see here, this Lorentz model is a chaotic system. And then we will check the performance for the filtering method by comparing the mean, the average value of the posteriors, and the true observations generated. And so here are two examples for the filtering. In the first one, we plot the mean of the posteriors calculated by the Kalman-adjusted KME-dynamics and in simple Kalman filter respectively, and compare them with respect to the true observations. As we can see, at some point, the in simple Kalman filter lost the track of the chaotic system, but the KME-dynamics works very well all the way, even when the number of particles is not so much. And similar, this applies also similarly in the Lorentz 96 system. In this plot, we take the dimension of sample space to be 10. So this means the KME-dynamics also outperform the in-symbol Kalman filter in high dimension. And so to make the experiments precise, we also do some benchmarks. So we calculated the root mean square error between the mean of the posteriors and the true observations. And we adjusted the parameters of our method a lot and the settings of our experiment a lot, and make some benchmarks here. So in the first plot on the left-hand side of this slide here, we show we use a very large model error for the Lorentz system. As we can see, when the model error is very large, all of the method performs very stable. And as we can see, the kernel mean the KME-dynamics can outperform the in-symbol Kalman filter very easily when we take small regularization terms. So here the regularization is a small regularization we introduced in the inverse problem before. And here the root mean square error, which means so if the root mean square error is smaller, the performance of the filtering method is better. So so now in the middle plot here, we can so before I go to the second plot here, so why we change the model error to be smaller? That's because if we use a large model error in the Lorentz system, we would expect that all of the posteriors are almost Gaussian, that somehow lose the advantage of KME-dynamics in the nonlinear case. So that's why we would like to check what will happen if the model error is very small. So we take a smaller model error and make some experiments. As we can see here, all of filtering methods get more unstable. And as we can see here, if we take a larger regularization, we can make it more stable, but we also introduce some errors into the linear systems. So the choice of the regularization is a trade-off. So in this case, for KME-dynamics, it's very hard to find the best regularization to outperform the in-symbol Kalman filter. But somehow, if we use the Kalman-adjusted KME-dynamics, one of the extension we introduced before, we can easily outperform the in-symbol Kalman filter by just choose a very large regularization, like here. So as shown in this last plot on the right here. So if we take a large regularization, and it's very stable and outperform the ensemble Kalman filter. So that's almost all of my talk today. And to conclude, we built a new algorithm called KME-dynamics. From the perspective of dynamics of kernel mean embeddings in continuous setting. And we built two extensions to the KME-dynamics called the Kalman-adjusted KME-dynamics, which is very useful when we have some pre-knowledge about the filtering. And another one, the important sampling KME-dynamics is generally a good choice for saving time steps. And finally, we believe that KME-dynamics could be a very powerful tool in the future for the studying on the hidden Markov model. So before I end this talk, I would like to refer some relevant literature about, to the KME-dynamics. So first, if you would like to check more theoretical details and numerical details about our work, please, you can see our paper. Though it's the old version, however, we will update it very quickly these days. So secondly, Amy and Yusuf, they also formulate almost the same method as KME-dynamics, but they formulate this algorithm from the optimal transport perspective. And finally, so the kernelised diffusion map paper written by Bach and Lucas is about the functional analysis about the kernelised diffusion operator. Actually, the KME-dynamics can also somehow formulated by this kernelised diffusion operators. So that's all for my talk today. Thank you very much.
Yeah, thank you very much. Thank you.
Yeah.
Any questions, comments?
Oh, hello.
Yeah.
Oh, thanks for the talk. Okay. Yeah, two questions, but one is that whenever I regularization of adding epsilon, I got a little bit nervous. So because if you don't have the ensemble Kalman to compare against, if we're just solving this problem, no problem, then we will be hard pressed to know what's the epsilon we should use, right? So I don't know whether you have thoughts about other kind of regularization, but this is just a general comment. Yeah, because to use it practically, I'm not sure this is we can just use it like in this form. This is just from a practical person point of view. Yeah. The other is a paper I read from the NIPS 2019. I post in the chat. Okay. That paper, it could be very valuable for to your problem. Yeah, it used L1 geometry, and it argues that in L1 geometry has a property that is more attractive to solve this problem than, just the kernel 2 sample test problem than using L2 geometry. So, yeah, I'll be curious if you look at it and see whether you feel this can be can be something that you can add or supplement what you are doing. It will be very interesting to hear your comment. Okay, thank you.
Yeah. Okay, thank you very much for sharing this information. I will check it later. Yeah, for this regularization term, we it's a trade-off. So it's still very hard to find the best regularization yet. Yeah. Yeah.
Maybe Mani, do you have specific regularization schemes in mind that work, that I don't know, for some reason might work well in a problem like this?
In general, I come from the optimal transport and fluid flow point of view. So, I would try, I tend to penalize the smoothness, the lack of it, of the velocity field, that kind of stuff. I don't know. I don't have a specific recommendation, but I just feel we need to go beyond epsilon. Yeah.
Okay. Thank you so much. I think it's very valuable. Yeah.
Yeah, that's cool direction.
All right. Any other questions or comments?
I have a simple question. Is it possible to make every step of the time series to calculate the KL distance between the posterior and the prior, and from this to learn something and see if there is a difference between the KL distance capacity versus the other approach, like the RKHS that you have used?
Sorry, can you say that again? I'm not sure.
You have a time series, right?
Yeah.
As you go from the prior to the posterior. Now, in every step, you mentioned also some doing things every step. I suggest, or I consider, calculating at every step the KL distance, Hilbert-Leiber distance, and maybe this can simplify part of the other machinery that you have used.
So for
Hilbert
KL
KL distance is a difference between two distributions. It's a distance.
Yeah,
okay.
I mean, for this, for each time step, which two probability distribution should I compare? I mean,
yeah. Because we are evolving given distribution, like the prior, we are evolving. Actually, it's not even given in your talk, but you use the Kalman somehow to get empirical. Anyway, I don't want to confuse you with my words here. It's just an idea. I will have to look at it. And I hope the recording also included that paper that was mentioned by before in the chat.
Yeah. Okay. Thank you.
Okay. Thank you very much.
Yeah.
But just on I studied this problem quite a bit, but just a comment, KL is not a distance. Okay. So KL is not very good at measuring the distance between two distributions. It's because it's not a metric, and it's also not symmetrical. So it's really problematic. Yeah, it's a divergence. That's really why people like us tend to want to use Wasserstein or optimal transport to measure distances between distributions. Yeah, but anyway, yeah, because of KL divergence have a problem if the two distribution does not overlap or support, or only partial, very little overlap, which in high dimensional is almost always highly probable. So it has a singularity. So that is another problem with KL divergence. Anyway, okay, thanks.
Yeah, thank you so much.
Thank you.
All right, thank you very much. Other comments or questions?
Yeah.
Yeah, so was there someone who wanted to ask a question or comment? All right, okay, seems not. Okay, thank you again, Linfeng, and thanks everyone for attending. And,
yeah, thank you so much again.
Yeah, see you, bye-bye. Thanks.
Yeah, have a nice day.
Thank you.